Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to learn 12th module, 4th lecture, that is 59th lecture of this course. As we have seen in the previous 4 lectures, we have been talking about the applications of numerical linear algebra in real life systems, how they do come up with the matrices, solutions, and then physical interpretation. In continuation to that, today we are going to learn few more things which would enlighten us how numerical linear algebra would play a vital role in real life systems via solving the matrix equations. All of you knowing very well, let us start with simple boundary value problems. You look at over here, u is a function of x from this equation. So x is defined at 0, u is 0, x is defined at 1, u is equal to 1. So you have minus u double prime plus pi square of u will be equivalent to 2 pi square sine of pi x. Comparing this problem with the prototype problem, we see that px is equal to 0, qx is equal to pi square, and rx is equal to minus 2 pi square sine pi x. Since px is equal to 0, we are guaranteed of a unique solution to the finite difference equations for any value of the spacing h. So look at over here, x is from x naught is 0 starting value and x terminal value is, I can call it as 1. So one segment, second segment, third segment, fourth segment. So this is 0.25, this is another 0.25, another 0.25, another 0.25. This is what is called computational template at this one-dimensional grid point. Let us start with uniform partition of the interval 0, 1, containing n is equal to 4 subintervals. Then h is equal to 1 over 4 and the grid points are given by xi will be equivalent to aih, that is equal to 0 plus I times of 1 over 4, that is equal to I upon 4. This partition is illustrated in the below figure as we have seen over here. Evaluate the differential equation at the interior point x is equal to x of I and then replace the second derivative by its second order central finite difference approximation. So you write it as u of I minus 1 minus 2ui plus u of I plus 1 divided by, that is 1 over 4 square with minus signature, plus order of h square plus pi square ui. So which will be 2 pi square sine of I pi by 4. Next we drop the truncation error term and replace each ui, which is a value of the exact solution, by wi, which is a value of the approximate solution. Multiply both sides of the resulting expression by 1 over 4 whole square and yields the computational template. So you will have minus of w of I minus 1 plus 2 plus pi by 4 whole square times of wi minus wi plus 1 will be equivalent to 2 times of pi by 4 square sine of I pi by 4. Sine of I pi by 4. Writing out the equations that corresponds to I is equal to 1, I is equal to I is equal to 3, and combining these with the equations W naught is equal to 0 and W of n is equal to 0, which are derived from the Dirichlet boundary conditions. The complete system of finite difference equation will take it to the form. So this is how you do get, this is how you do get, and this is how you do get it. So rest are all zeros. The solution of this tridiagonal linear system is W is equal to 0, 0.725371, 1.025830, 0.725371, 0 volt transpose. The following table compares this approximate solution with the exact solution. So you will have u of x is equal to sine of phi x. The accuracy of the approximate solution is quite reasonable given the crudeness of the computational grid. So xi, approximate solution, that is wi, and exact solution is ui, and this is the absolute error. Anyway, in this case it is 0.0000, no meaning. When x is equal to 0.25, solution is 0.72531, exact solution is this, and the difference is this, 0.018264. Similarly, when h is equal to 0.5, so approximate solution is, looks like 1.025830, and this is the exact solution and this is the absolute error. When x is equal to 0.75, so this is the approximate solution, this is the exact solution, and this is the difference. So when xi is equal to 1, and this is the thing, and so you get a value 0.000000. A numerical verification of the second order accuracy of the scheme is presented in the next table, which displays both the maximum absolute error and the root mean square error in the approximate solution as a function of the number of subintervals n. The RMS error was computed according to the formula. So this is, so RMS error is 1 over n summation I is equal to 1 to n minus 1 wi minus ui square under square root. Note that with each doubling of n, the step size is cut in half and the approximation error is reduced by roughly a factor of 4, which is what one would expect from a second order numerical method. The finite difference approximation obtained using n is equal to 32 is shown in the figure below, denoted by the diamonds superimposed on the exact solution. So like this. So you will have a x in this direction and you will have ux in this direction. So you will have this, you will have this. So like this will go, like this will go. So this is the exact and this is the approximate solution. Comparison between the exact solution to the boundary value problem, that is minus of u double prime plus pi square u will be equivalent to 2 pi square sine pi x, that is u0 is equal to 0, u of 1 is equal to 0. and the finite difference approximation generated with the uniform partition containing 32 subintervals as shown over here. So if you look at this n and maximum absolute error, error rotation and RMS ratio and error ratio. So when n is equal to 4, you look at 4. So this is the maximum absolute error, 0.0258 297765. So this is the RMS ratio which you get it. When n is equal to 8 and 0.0064337127, and this is the ratio tau. This is the RMS ratio, like this you do get. When n is equal to 16, this 0.00160689. This is the error tau, RMS, and this is the ratio. When n is equal to 32, and this is 0.0004016275, and this is the error ratio, you do get it. When this is 64, so this is the, when you get it, maximum absolute error is the error ratio, and this is the error ratio which you get it. When n is equal to 128, and this is the error ratio, you do get it. When n is equal to 256, and this is the error ratio, you do get it. So when n is equal to 512, you do get the error ratio like this. So as a second example, consider the boundary value problem. You have a boundary value problem. So u0 is equal to -1 and u of 1 is equal to 0. So look at over here, it's again a linear case. As you see that u0 is -1 and u1 is 1, and the boundary values are, the boundary condition specified has no nonlinearities. Similarly, this equation also has no nonlinearities. For this problem, we see that px is equal to -x plus 1, whose maximum absolute value in the interval is 2. Hence, we are guaranteed of a unique solution to the finite difference equation for any value of h less than 1. So let us use the same partition as the previous case, that is, divide the interval 0, 1 into 4 subequal intervals, that is, h is equal to 1 over 4 and xi is equal to 1 over I upon 4. Applying the computational templates, you write -1 minus h by 2 times of pi multiplied with wi minus 1 plus 2 plus h square qi wi, and like this you do get it. For I is equal to 1, 2, 3, you will have this set of equations. And including the equations, that is w0 is equal to -1, sorry, w4 is equal to 0. So obtained from the boundary conditions, we arrive at the following system of finite difference equations. So you will have the like this, and you will have like this, and you will have like this, and 0. This is 0. So ultimately you will have w0, w1, w2, w3, w4. So you will have the equations like this. The solution of this system would become like this. This is the one which you get it. W is equal to -1, that is minus of 0.582559, minus of 0.301452, and this is the minus of 0.116906, which compares favorably with the exact solution, that is ux is equal to, that is u of x is equal to, you do get as x minus 1 times of e power minus x. As shown in the following table, a numerical verification of the second order accuracy of the finite difference scheme is left as an exercise. So you will have xi 0, 0.25, 0.5, 0.75, 1, and these are all approximate values, minus 1.0, minus 0.5825, yes, this thing, this value, and this value, this value, this value, this value, this value. So you will have like this values. So when you do this, so this is in the x direction and this is in the ux direction, you get like this. So it goes like this. So exact solution, approximate solution, they would be matching very well. So this is the comparison between the exact solution to the boundary value problems, that is u double prime is equal to minus of x plus 1 times of u prime plus 2 times of u plus 1 minus x square times of e power minus x, and u0 is equal to minus 1, u of 1 is equal to 0. The approximate solution obtained using a uniform partition with n is equal to 32. subintervals as shown in the above figure denoted by diamonds superimposed on the exact solution. Finite difference method, the linear problem with the non-Dirichlet boundary conditions is, consider the prototype one-dimensional two-point boundary value problem, that is y double prime is equal to px times of y prime plus qx times of y plus rx, where x belongs to, that is a comma b. So you have a y of a is equal to alpha, y of b is equal to beta. So you apply the non-dimensionals and ultimately you get steady state conditions of heat in the metal rod. So you get the Dirichlet boundary conditions which corresponds to prescribed temperatures at the end of the rod. In practice, however, the temperature at each end of the rod might not be known. For example, we might only know that at the end x is equal to b was inserted so that there was no heat flux from the end. So this would give rise to a boundary of the form y prime, that is y of prime of b is equal to 0. The boundary condition of this form, in which the value of the derivative is specified, so that is known as what we call the Neumann boundary conditions. So the heat transfer is taking place at the end x is equal to a, so this would give rise to a equation of the form minus k times of y prime of a will be equivalent to h times of T infinity minus y of a, where k is the thermal conductivity of the rod and h is the convective heat transfer coefficient between the rod and its surroundings, and T infinity is the ambient temperature. So T infinity is the ambient temperature. A boundary condition of this type, in which a linear combination of the values of the function and the values of the first derivative is specified, which we call it as the Robin boundary condition. So in this lecture, we investigate the formulation of the finite difference method for linear boundary value problems, and ultimately when you get these equations, you do end up with the what you call the matrices, and these matrices will give us what you call this numerical linear algebra. How to find out those methods would be applicable. Non-Dirichlet boundary conditions, because the general Neumann boundary condition is you have it y prime of a is equal to alpha, y prime of b is equal to beta. It's just a special case of the general boundary condition, Robin boundary condition. So that is the most generalized case is alpha 1 times of y of a plus alpha 2 times of y prime of a is equal to alpha 3, or beta 1 times of y of b plus beta 2 times of y prime of b is equal to beta of 3. So when you set up this alpha 1 is equal to 0 and beta 1 is equal to 0, we will develop the system of algebraic equations for the finite difference approximation to the linear boundary value problem. That is, you will have it y double prime is equal to px times of y prime plus qx times of y plus r of x. So x belongs to the case a comma b. So this is what is called the Robin boundary conditions. Alpha 1 times of ya plus alpha 2 times of y prime of a is equal to alpha 3, and beta 1 times of y of p plus beta times of y prime of p is equal to alpha 3. So this is what is called the Dirichlet boundary conditions. For the computational grid, let n be a positive integer and partition these intervals into the a is equal to x0 less than x1 less than etc. less than x of n is equal to b. So where this x of I is equal to a plus I times of h, and h is equal to b minus a upon capital N. Further, let Wi denote the approximation to the exact solution. So we need n plus 1 equations to determine the values W0, W1, W2, Wn of these equations are obtained as the previous lecture. So evaluate the difference equation at each grid, so we could able to obtain these equations. So the resulting computational template is essentially will become minus 1 minus of h by 2 times of pi w of I minus 1 plus 2 plus h square times of qi times of wi plus minus 1 plus h by 2 times of pi w of I plus 1 will equal to minus h square r1. The only remaining question is what we do at x0 is equal to a and xn is equal to b. Let's focus on the treatment of the boundary conditions at x0 is equal to a and this equation will be, to maintain the second order accuracy, so we will be obtained these equations. So essentially you will have yi prime will be approximately equal to minus of 3 yi plus 4 times of yi plus 1 minus of yi plus 2 divided by 2 of h. Unfortunately, this would destroy the traditional structure of the coefficient matrix. Using a first order forward difference formula would maintain the traditional structure of the coefficient matrix, but would degrade the accuracy of the overall approximation, as we could see from the results. A third possibility which will maintain both the structure of the coefficient matrix and second order accuracy of the approximation is fictitious nodes. How you define the what you call the fictitious nodes? So fix that for particular nodes that and then try to adjust it. Applying the computational techniques for the differential equations produces x is equal to x naught, produces, that is minus 1 minus of h over 2 times of p naught wf plus, that is 2 plus h square times of q naught times of w naught plus minus 1 plus h over 2 times of p naught w1 is equal to minus of h square r naught. So Neumann or Robin boundary conditions specified at each, that is xf and x of 2. So this is the segment, this is the segment, and this is the segment. That's the computational domain we have. This is accomplished by applying the Robin boundary conditions. So you will have alpha 1 times of y of a plus alpha 2 times of y prime of a is equal to alpha 3, which implies alpha 1 w naught plus alpha 2 times of w1 minus wf divided by 2h, which will give you alpha of 3. So where we have replaced the first derivative with its second order central difference approximation, solving this last expression, so you get as w of f is equal to w1 minus 2h upon alpha 2 times of alpha 3 minus alpha 1 w naught. Substituting this relation into equation 1, we obtain the finite difference approximation associated with this expression. So ultimately we will end up with w naught w1 and the alpha 3 and alpha 1. So when you apply this Neumann boundary conditions with alpha 1 is equal to 0, so alpha 1 is equal to 0, the corresponding finite difference equation would be read as, that is 2 plus h square times of q naught, that is w naught minus 2 w1, which will be equal to minus of h square r naught minus 2 plus h p naught times of h of alpha, where we have written alpha for the ratio alpha 3 by alpha 2. So alpha 3 upon alpha 2. Performing a similar analysis for a Robin boundary condition at x is equal to b, so this equation would fit into this form like this. So we now have all n plus 1 finite difference equations. Having started form a linear differential equations, the resulting algebraic equations are linear in these unknowns, that the finite difference equation can then be written in the form, that is a times of w is equal to b, and w is equal to w naught, w1, w2, wn whole transpose. So when you apply this in terms of matrices, so you do get the matrix like this. This is the matrix, and this is the one diagonal, and this is the another diagonal, and this will become a 0, and this will become 0, and the matrix B will be of this form. So di is equal to 2 plus h square times of qi, and ui is equal to minus 1 plus h by 2 times of pi, and L of I is equal to minus 1 minus h by 2 times of pi. So this ai1 is equal to 1 for the Dirichlet boundary condition at x is equal to a, and 2 d naught Neumann boundary condition at x is equal to a, and d naught plus 2h L naught alpha 1 by alpha 2 Robin boundary condition at x is equal to a. So you get this equation a of 1, 2. So this can be written as an plus 1 comma n plus 1. So ultimately you will have an plus 1 comma n plus 1 matrix would be taken to this form. So that is the one when the Dirichlet boundary conditions at x is equal to a is imposed, and d of n that is Neumann boundary conditions when at x is equal to b is imposed, and dn minus 2h un b1 beta 1 by beta 2 Robin boundary conditions when you apply at x is equal to b. So essentially you get as a n plus 1 comma n, that will be equivalent to 0, that is Dirichlet boundary conditions at x is equal to b, and it is a minus 2 otherwise. So b1 you get it as alpha, that is minus of h square r naught plus 2h into L naught of alpha Neumann boundary conditions, and minus h square r naught plus 2h L naught alpha 3 by alpha 2 Robin boundary conditions at x is equal to a. And bn plus 1 will become a beta, so that is what x is equal to b, and Neumann boundary conditions at x is equal to b. So this is what is called the boundary conditions which we try to see it. So there are several examples when you try to do it, and a problem with one Neumann and one Robin boundary condition. This is a very typical example which we come across in many engineering systems. And consider this differential equation u double prime plus u is equal to sine of 3x, where x belongs to 0 pi by 2. So this is what is called Robin boundary conditions. U double prime plus u is equal to sine of 3x, x belongs to 0 pi by 2, and Robin boundary condition is u0 plus u prime 0 is equal to minus 1. So that means at x is equal to 0 this is defined, and at x is equal to 0, that is u of 0 is defined and u prime of 0 also defined. And the Neumann boundary condition x equal to pi by 2 is u prime of pi by 2 is defined as a 1. So this is a combination of mixed boundary conditions. So let us take a uniform partition of 0 pi by 2 with 4 subintervals. Then h is equal to pi by 2, so that h is equal to pi by 8, and xi is equal to I times of pi by 8. For I is equal to 0, 1, 2, 3. Comparing the given differential equation with the prototype, we see that p of x is equal to 0 and q of x is equal to minus 1, and r of x is equal to sine of 3x. Therefore, for each pi, you will have pi is equal to 0, qi is equal to minus 1, and ri is equal to sine of 3 pi I by 8. Further, for the Robin boundary condition at x is equal to 0, we have alpha 1, alpha 2 as a 1, and alpha 3 is equal to minus 1. Finally, with the Neumann boundary condition, so x is equal to pi by 2 and beta is equal to 1. So we could able to achieve this matrix in the form of. So further, as you see that and all, this has become the, this is the main diagonal element, and this is the sub-diagonal element, this is the super diagonal element. So these are all zeros as we see here. W0, W1, W2, W3, W4, and this is the forcing vector, where this d's are nothing but this expression 2 minus pi by 8 whole square. So in the first and the last entries of the right hand side vector, we have used the fact that sine of 0 is equal to 0 and sine of 3 by 2 is equal to respectively. The solution of the trigonal system will become like this into this form. The following table compares this approximate solution with the exact solution. Ux is equal to, so u of x is equal to minus of cos x plus 3 by 8 times of sine of x minus 1 over 8 times of sine of 3x. The accuracy of the approximate solution is quite reasonable given the crude approximation of the computational domain consideration. So if you see from the table, you could able to get into the comparison for xj is equal to 0. So this is the wi and this is the ui, and this is the absolute error. And for xi is equal to pi by 8, and this is the wi, this is the ui, and this is the error. For xi is equal to pi by 4, and these are the values you do get it. For xi is equal to 3 pi by 8, these are the values you do get it. Pi by 2, these are the values you do get it into these equations. So a numerical verification of the second order accuracy of the scheme is presented in the table, which displays both the maximum absolute error and the root mean square error was computed according to this formula, that is RMS error of this form. Note that with each doubling of n, the step size is cut in half and the approximate error is reduced by roughly a factor of 4. So which is what one would expect from the second order numerical schemes. So from this lecture, what we learned is, when you try to model this differential equations with initial and boundary conditions, ultimately you will end up with the what you call tridiagonal matrices with some kind of errors we will see from these examples. You see from this example also, you could able to obtain this, this maximum error and the error ratio and RMS or root mean square error, which will give you the more implication about the error occurring and the error propagation, how it should be controlled for the differential equations for the different values of the capital N. So from this lecture, what we have learned is how these, the numerical algebra would be useful for solving the real life systems, and for solving the trigonal matrices. We know that there are standard algorithms available like Thomas algorithm and so on and so forth. Thank you very much for listening to my lecture today, and tomorrow I will be giving you another lecture, last lecture, would be closing session of this course, Numerical Linear Algebra and Applications. Thank you very much for being with me for this lecture. Thank you once again.